So this is such an interesting story. If you get a chance to read your textbook or look further into this whole Copernicus, Tycho, Kepler, Galileo thing, these are historic people in understanding things about our solar system long time ago. But we have kind of this passing of the baton or passing of the torch. Tycho Brahe, as I understand it, was and there's kind of a little picture of him down here. Or I don't know, that might be one of his assistants. But he was, oh, that looks like as an assistant. He looks more important. He was a nobleman who had a lot of money and kind of toyed around with observations. Without a telescope, and you can kind of see his like fancy little degree thing here. He actually would plot things in the nighttime sky and make observations. Again, without a telescope, great notes, right? And one of the things he watched these wanderers. He watched planetary motion, and so he would get the direct motion and the retrograde motion and try to kind of make sense of it. And he was working he was working with probably the Copernicus model at that point, the sun-centered model, but he again struggled with a little bit of the detail of these wandering planets. They didn't quite fit the math didn't quite fit a sun-centered model. So he actually hired Kepler, who was a little bit better with regard to crunching numbers. That's the way I think of it anyway. So Kepler then actually used Tycho Brahe's observations to come up with 3 important laws about how the planets move. We call them planetary laws of motion. So Kepler actually, when he took Tycho Brahe's raw data, like most scientists, he had to kind of mull it over. You can't change your observations, your raw data, but you can look at it different ways. So in trying to force fit it basically to circular orbits, trying to force fit it to circular orbits, it just wouldn't work. It wasn't lining up with the observation of the planets versus these circular motions. But if you go ahead and make the shape of the orbits elliptical, and I'm going to tell you what ellipses are ovals. I just thought of Ovaltine there, but ellipses are ovals. What an oval is actually a circle is a type of an ellipse, but ellipses can be flattened. Okay, those are examples of ellipses. He said that if you go ahead and have the planets, including the Earth, orbit the sun in shapes of ellipses, then Tycho Brahe's data matches up great. And so that's actually what he went with, and that's actually the reality of the situation. So let's take a look at what Kepler came up with then with regard to the planets and their motion as the planets orbit the sun. So Kepler's first law, and again, this is a little controversial because remember I said that the planets in the heavens and the star in the heavens, it's all about circles or spheres. It has to be perfect. And so this ellipse it's weird to think it would be that big of a deal, but it was a kind of going against what the church thought at the time. So here we see, can you see that this is an ellipse? Okay, and here's an ellipse. It's just kind of an oval. Now, there are some features about an ellipse that you need to be aware of. Ellipses have 2 foci. Here's a foci, and here's a foci. Can you kind of see those circles? Okay, 2 belly buttons. Now, the foci actually can be identified. I kind of like this figure over here. If you go ahead and take a string, and you go ahead and kind of take your pencil and run it around like that, you can go ahead and create an ellipse, and that's how your foci are. Other parts about ellipses is from the center, which there's nothing necessarily in the center of an ellipse or an oval, from the center out to the edge of the greatest way you can go is called a semi-major axis. And then we have, okay, so I guess one other thing I need to kind of mention, I haven't mentioned it yet, okay, and it has to do with actually coming up, is that, do you see where the sun, according to Kepler's first law, is not only the shape of the orbits of the planets, but the sun as at one foci. So that's the sun right there. It's at one foci. So if it's at one foci instead of center, do you see where as the planets orbit the sun, sometimes they are closer to the sun, and we call that perihelion, when a planet is closest to the sun. When a planet is farthest from the sun, over here, we call that aphelion. So those are two important kind of outcomes, or several important outcomes of Kepler's first law, the shape of the orbit of the planets. Now his second law, I'll explain it and then I'll tell you what's so important about it. Kepler's second law said that if we make this time, I'll make this T1, the time it takes to go from A to B, we're going to call that T1, and we're going to call over here, we're going to call this T2, the time it takes to go from C to D. Okay, we have and by the way, it's all about actually counterclockwise. So planets orbit the sun counterclockwise as you're looking down at their north poles. So those two times, if those are equal, then these areas, if you take from their positions and go back to the sun and make like kind of like a triangle, like a wedge, take their positions and go back to the sun, make a wedge, those two areas are the same. Those two areas are equal. Okay, it's basically, we say that a planet will sweep out equal areas in equal amounts of times. Well, here we go. You guys would probably tell me this is longer. T1 is longer. I would say longer. The distance is greater. Okay, D is greater. Does that make sense? Okay, and here distance is less. D is less. So my only point here is if it's the same time, do you see where if distance is less, the same time, this, bottom line, this is going slower. Okay, and that means that distance is greater the same amount of time, that means this is going faster. That is a big, I think, kind of a big hairy deal. If we use kind of what we call the Doppler effect we talked about before, here it's going, if going from A to B goes, it goes meow, okay, it's going fast, and here it goes meow, kind of goes slow up there. So anyway, planet swings faster as it's near perihelion, fastest at perihelion and slowest at aphelion. The last one, actually, I don't know what to say about it. I'm just going to kind of throw it up there. Remember when we talked about retrograde motion, I said that the Earth travels more slowly in its orbit than Mars. So actually, right here, we could check that out. Okay, sidereal period is how long does it take the planet to complete one orbit about the sun. So here we have relative to Earth years. If we find the Earth, of course, it takes 1 Earth year. If we find Mars, it takes almost 2 Earth years, 1.88 years. And you might say, well, yeah, Mars has a bigger oval. It has a bigger ellipse to complete one orbit. But it's not just that. Literally, it travels more slowly in its speed. Okay? So that's, to me, the biggest thing, and it's summarized up here. More distant planets orbit the sun at lower average speeds. Now, he actually did something that we do a lot in science. We look for relationships. So what he did was basically take the period squared, that's what P is, and he said that's equal to the its average distance from the sun cubed. And he found that relationship. But again, bottom line is the closer the planet is to the sun, one way to look at it is that the faster it moves.